All right, so last segment of the workshop, keeping with the theme of today, new directions in crypto. Rafael will tell us about all the amazing work that's happening in crypto and meta complexity in the intersection.
Excellent. Thank you so much. And thanks all for staying so late. And I hope it was a fun week. It certainly was for me. And I'm really glad to give the last talk of the week. So as you heard, I'm going to talk about cryptography and meta complexity. Roughly speaking, meta complexity is a branch of complexity theory that is about the computational complexity of problems that themselves talk about complexity. I'm going to mostly focus on the problem of Kolmogorov complexity, okay? But I'll tell you, many of these results work more broadly and extend to other problems that are related to this. I will discuss some of that, but most of the time I'm going to talk about this notion of Kolmogorov complexity. But before jumping into Kolmogorov complexity, let me motivate why I am interested in this connection between cryptography and Kolmogorov complexity. And it goes back to really the most basic question that we are all here interested in. Do we have secure encryption schemes? Right? If I want to have secure private key encryption or key exchange, do they exist? Right? And as we know, today we rely on computational hardness assumptions in order to get these primitives. Why? Well, because in order to prove the existence of secure encryption, that already requires proving that P is not equal to MP, because if P is equal to MP, then we can break all of these primitives. Right? So today, we live in a world where we rely on these primitives all over the place. Right? Every time I use my cell phone, we rely on it. But we don't know that they actually exist. We rely on computational hardness assumptions in order to achieve them. And these computational hardness assumptions today fall into three categories, roughly speaking. Okay. We have number theoretic assumptions. We have number theoretic assumptions such as factoring, discrete log, and there are some more in that class. We have something referred to as noisy linear algebra assumptions. These encompass lattice assumptions, and most notably learning with error. And then we have some heuristic type assumptions like AES and SHA and so on. This is when we talk about private key encryption. When it gets to key exchange, the situation is actually worse. We don't have this last third class of assumptions, and we only have these first two classes of assumptions. As we heard earlier in the workshop, if quantum algorithms are built to scale, then most of these guys are actually gone. Right? That's not entirely true what I said, because as you heard, there are also these class group assumptions that maybe would survive, but the situation is kind of iffy with respect to number theoretic assumptions. These guys seem to be fine at the moment, but as you also heard from Mark, they haven't been around for that long, and so we don't really understand them as well as these guys yet. Furthermore, in the recent year, as you've heard this morning, there's been another trend that's been going on, and that's that of machine learning-based algorithms. Now, machine learning-based algorithms, they're typically very good at doing one particular task. If you have something you can do exactly, they're able to solve noisy versions of that. And that's, in essence, the type of hardness we're relying on here. Now, I'm clearly oversimplifying. Machine learning is good at doing it when we have some kind of continuity, and that's something we are lacking here. But maybe some gadgets can be used to transform these things into something that those things can solve. And indeed, there had been some work from a few years ago trying to do it. I am not very familiar with this vein of work, but there is some claims that maybe machine learning algorithms could be used in order to get us close to the state-of-the-art algorithms, at least for certain subclasses of problems. And another kind of disturbing thing that's been going on here is that machine learning, these most recent LLM-based algorithms, they're actually very good at finding these gadgets that people used a lot of human ingenuity to find before. So these things are, at least in other domains, are beating state-of-the-art algorithms, like in particular in NLP. These general purpose algorithms are doing much better than what we knew how to do with very, very beautiful and delicate analysis before. It's just blown out of the water. So it would be good if we had alternatives. And that's where Kolmogorov complexity will come in. I will try to hope to at least convince you that Kolmogorov complexity can be viewed as a new pillar of assumptions, and maybe a very nice area from which we can get new assumptions that maybe will be robust to these type of attacks that we have. I'm going to talk about both the setting of private key encryption and a little bit about the setting of key exchange or cryptomania. And in the setting of private key encryption, what we'll see is that, in fact, there exists a very natural assumption, an assumption that goes back to the 1960s, called the hardness of the so-called time-bounded Kolmogorov complexity problem. That if you assume that this problem is actually hard on average, then that's equivalent to the existence of one functions. So that's quite different from the type of results we had before, where we had hardness assumptions that imply private key encryption, but they're not implied by it. They're not equivalent to it. Here, in contrast, actually, this assumption will turn out to be equivalent to private. And there will be later on a similar type of result also in the setting of key exchange. Here, the assumption, to be completely open, is not as natural and not as old. This is going to be a new assumption, but I hope to convince that it's kind of a natural generalization of this problem. Now, what's cool about these problems is they're seemingly unstructured. There doesn't seem to be any mathematical structures that give us a handle for how to break them easier. In particular, as we'll discuss later on, these problems were actually originally studied for the fact that they seem to be super hard. They seem to resist anything except brute force attacks. And then, as I mentioned, they're not only sufficient, but also necessary for secure instantiations. And that's what's different from previous results.
You were saying that they were studied before P and NP.
Actually, they were studied before P and NP. Yes, we'll get back to that, yeah. So these are, as I hope to convince you, they're very natural problems. Actually, the connection with cryptography will elucidate these problems a lot also. And that's what I hope to convey here too, that actually, even if you don't care about cryptography, if you're a complexity theorist and you're interested in just these problems, the connection with cryptography has actually in recent years elucidated these problems a lot, and we have uncovered new and intriguing properties about these problems that show that these problems themselves actually are really quite unique. They have certain properties, like actually some notions of random self-reducibility, that we don't know other problems having. Okay? So there will be new insights, in fact, to both meta-complexity and cryptography. And the insights into cryptography will be quite far-reaching. It's not just about these primitives. They will extend actually to tasks such as zero-knowledge proofs and I/O also. And so I hope to actually cover all of that. Okay. So at this point, we're ready to jump in, and let me tell you what Kolmogorov complexity is. Okay? Let me just be upfront here. I'm going to explain results here, not in chronological order at all. Okay? I'll try to kind of explain it in more of a conceptual, taking a conceptual viewpoint. So these proofs sketches that I will give don't really exist in papers. This is kind of like having been reordering things in order to convey them in the easiest possible way. Actually, before introducing Kolmogorov complexity, let me just give you kind of a glance of what kind of connections this gives. Now, to me, the most interesting question in cryptography and most important is whether we can get one-way functions or private key encryption from NP not equal to P, right? That would be, and that's why it's called actually, the holy grail is the question that came from Diffie-Hellman in 1976. We know that one-way functions imply that NP is not equal to P, but can we also get one-way functions from this? Now, based on this connection with Kolmogorov complexity, this question actually reduces to doing two things. Okay, proving that Kolmogorov complexity is NP-complete, which we'll see later on is a question that's been studied a lot since the 1960s, okay? And second of all, showing that there is a worst case to average case reduction for this problem. Again, a question that's been intensively studied. So this question that we care about a lot is actually very tightly related to questions in the complexity theory literature. So this is equivalent. The Holy Grail is equivalent to these two things.
But just to check, if you believe, I don't know, maybe you will tell us, but if you believe that this is not possible, does it indicate that there is some kind of, that this is kind of useless? And this is like, there is a syntactic similarity?
If you believe that this is not possible, well, you know, that maybe will tell you that maybe this is not NP-complete. I don't know. We'll discuss this in much more depth later on. And I'll tell you, like, we have reasons to believe this is not possible. Those reasons have all been broken today, okay? We've shattered them. So we'll discuss it later on, but the reasons we previously thought that this was impossible was because there were some kind of black box separations. Today, we have techniques that go beyond all those black box separations. Okay, so those issues are not present anymore. Okay, it doesn't mean that it's going to be possible still, but at least, you know, this type of vein of work has actually shown that we can shatter the reason we thought it was hard.
Need to come up with new reasons we think it's hard.
Maybe we can do that. And we'll discuss that later on, actually. And in fact, IO will be a type of reason. Towards the end, we'll discuss that.
IO is like the only thing that is not affected by people.
We'll discuss that too, you know? Yes, but yeah. Okay, what is Kolmogorov complexity? So Kolmogorov complexity is a beautiful notion that was introduced in the early 60s. The papers were published later because at that point, you know, it took a few years to publish things. Independently introduced by Solomon, Kolmogorov, and Shaitan. And at least for some of them, one of the motivation was the following. Look at the following two strings, okay? Which one is more random? Well, clearly, this one does not seem very random. This one is, seemingly, right? There's this fun story about forget about it. Okay. Richard Feynman. So Richard Feynman was a physicist, very famous physicist. Was actually teaching at Cornell. And one day he comes to class and he's like pacing around and he says, you know what? This crazy thing happened. You won't believe it. Amazing thing. And they're like, wow, what is it? Tell us. And like, on the way here, I saw this like white truck with the registration plate AZ7493. And can you imagine what are the chances out of the 10,000 or 100,000 cars in the state that I end up on exactly that car? And they're like, dude, this guy is like lost it, right? What's the? But clearly he was onto something, right? Why was it less special that he saw that particular car? Because it's true, out of the so many cars, he saw that particular one, right? And the chance of that is like 1 in 100,000 or whatever, right? And it just happened to him. Now, how do we make sense of the fact that that wasn't a very special event? That wasn't a very unexpected thing. Whereas if he had seen a car with AAA 7777, at that point, we were like, whoa, that is like really pretty cool, right? So the notion of Kolmogorov complexity, in fact, by answering these type of things, gets exactly to that problem. Okay, so we're very used to talking about the amount of randomness in distributions, but how do we measure randomness in a particular string? What does it mean that this string is actually random or surprising or not surprising because it's just fully random, or that something is actually pretty surprising? Exactly what Kolmogorov complexity does. It's defined as, this brilliant definition, it says the Kolmogorov complexity of string X is a length of the shortest program that outputs this string X. So, and if your Kolmogorov complexity is big, then we call you Kolmogorov random. And if it's small, then you're not random. So this thing has a pretty small description. All right, for I equals 1 to something, print 1, 2, 3. And this thing might not have anything better than just print 1, 7, blah, blah, blah. Okay? Now, an easy observation about Kolmogorov complexity is that the Kolmogorov complexity of string n, or of length n, can never be much longer than n plus some constant c. Okay, why? C is the length of, is 4, print. Fine, okay. Okay, so the Kolmogorov complexity of a string x can never be much more than the length of the string. Beautiful notion, has lots of really cool applications in logic, in mathematics, also in cryptography. You can give very nice proofs of certain things using Kolmogorov complexity. In fact, what Iftach started giving a high-level proof of, there is actually a very nice proof using Kolmogorov complexity that gives you the, not just for algorithms that are Paloma time, but also for circuits. So you can get like the tight bound in a very simple way using Kolmogorov complexity. Great notion, really fun to work with, but it's not computable, okay? Giving a string x, well, we cannot compute the Kolmogorov complexity of string x, okay? And that's easy to prove also. And that's really good if you want to prove some kind of incompleteness theorem, but it's not very good if your goal is to determine how much randomness there is in a string, okay? So Kolmogorov actually back then already noticed this in the last page of his paper. He said, look, you know, there are some issues with this, and we should also consider, in fact, a notion of time-bound or time-restricted Kolmogorov complexity. And that's just the natural analog where we restrict the efficient algorithms for computing this. So kt of a string x is the length of the shortest program that generates a string x within time t of the length of the string. Think of t as n squared, okay? For the remainder of this talk, basically think of it always as n squared. Okay, so I'm looking for the shortest program that will efficiently in n squared time generate this string. Like here's this Mandelbrot set is a kind of the classic example of something that has a very small time-bounded Kolmogorov complexity. There's a small Python program that's like this long that can generate this beautiful picture, and you can zoom in it also, and you can zoom in infinitely. It's super complicated, but has a very small program. Now, this thing is computable, okay? And not only it's computable, but if I tell you that the Kolmogorov complexity is 17, this is something that's in NP, right? Because I can give you the program, and you can just run it and check. This problem, after the work of Kolmogorov in his team there, this was intensively studied. There's a beautiful survey article by Trachtenbrot that describes all this research he did in the 60s. And intensively studied there, but really some of the key questions regarding this notion were still open. In particular, the question of whether this is, as I said, it's in NP, but is it NP hard? Is it NP complete? We don't know. And in fact, according to the methodology, Levin, who was Kolmogorov's student, when he wrote his thesis on NP versus P, Kolmogorov apparently asked him, like, oh, he's very nice, really beautiful, but now like proves that something meaningful is NP complete also. Sad, cool, but you know, let's do something that we care about. And apparently Levin postponed the publication of his like thesis for a year to study this question. He didn't succeed, and now, 60 years later, we're still stuck at the same problem, okay? So there's been a lot of amazing progress during recent years, and we're getting closer and closer, still open. This problem, and this is in fact one of the key reasons they were so interested in it from a computational point of view, was that this was a great candidate for something called a parabor problem. So parabor means apparently brute force in Russian, or brute force search. We don't have any better algorithm, essentially, than just, you know, if I give you X, how should you solve this problem? Well, you can enumerate all programs and just run them for n squared time. But essentially, we don't know nothing better. Okay? In fact, when it comes to uniform algorithms, we know still nothing better than that. And that's referred to as the parabor conjecture. So the parabor conjecture was an early precursor to NP versus P, still stands. Okay, so this is kind of like a super strong version of MP versus P. We still don't know how to disprove that. Okay, proving it will be better than proving MP is not equal to P, but this is closely related to something called the MCSP, which is another meta-complexity problem, the minimum circuit size problem. The minimal circuit size problem, you can think of it as exactly the same thing, but instead of talking about Turing machines that are generating strings, you would like to have a circuit. So you're looking for the smallest circuit. Okay. Today, I'm not going to talk so much about it, but as I mentioned, a lot of things that I will discuss actually do work for that also. Not everything, but many. Okay. Now, let me motivate why this, this problem is very natural if you care about the amount of randomness in distributions and so on. But there is something much deeper going on here, and especially in today's world. Now, in a world where KT is easy, and not only KT is easy, but let's assume that there is somebody who can find the smallest program for you. In that world, optimal fine compression is possible, right? Given X, I can find this best way to compress it. Cool, but it doesn't really change the world in a major way. I would like to, it's a little bit of a joke, okay? So bear with me. But in a world where KT is easy, if you believe in Occam's razor, I claim that science, in a well-defined way, would become easy, okay? There are some asterisks here, okay? But so what does Occam's razor say? Occam's razor says that if you observe some physical phenomena out there, or any phenomena, basically, what is the best way to kind of understand this, what happened? Occam's razor says, if you have two models that describe it, one that's much easier than the other, much simpler than the other, in that case, the simpler is the more true, is the truer. So in essence, if you would like to find the best explanation for what happened, find the smallest program that describes it, and that's going to give you the best explanation for it. So if we can solve KT and not only just compute it, but find the smallest program.
Small C program that describe the situation will help you understand.
Because you can continue running this thing, it's going to predict the future for you, right? If it describes what's going on here, it will probably describe also the future in the best possible way. Now, there's a lot of asterisks here. This was a little bit of a joke because we have noise data and so on and so forth. And of course, there'll still be reasons for doing science. We'll still be the slaves of the computers. We have to go and collect the data until there are robots that do it better than us. At that point, we will just stay home, watch TV. So, so at least I've hoped to convince that this is a very deep problem, maybe not as deep as MP or the MP versus P problem, because if MP is equal to P, then you can do this also. But this is inherently very interesting. If you could do this, it's much more revolutionary than if you could factor numbers, let's say, yeah?
You mentioned both the decision and search problem. Is there no search?
Great question. I won't actually talk about it. Oh, I wanted to give another, mention another thing. So Noam and I are writing a survey, or written it, that's going to be posted soon, that kind of discusses all of this and some more. But and there we discuss this question. So I won't have time to discuss it so much. In fact, in the 60s, they had a bunch of these questions that they were interested in. And the parabola conjecture was one of them. Another one was, is there a reduction between decision and search? What's going on? And in fact, there is no better, up until recently, there was nothing better than in fact doing brute force search also to do search, even if I have a decisional oracle. In recent years, in the work with Noam, we managed actually to get an algorithm that it's still not polynomial time, but it's better than brute force search. Okay, so there has been some recent progress on that. Still a great open question to do it fully. Okay. All right, so far we talked about just the problem and the kind of the worst case version of it, what happens if you can solve it always. In the 60s, actually, it's quite intriguing. This was before modern complexity theory was around. They actually also considered some notion of average case hardness. They didn't call it average case hardness. They called it the frequential version of the problem. So they asked the following: does there exist an algorithm that computes KT for a large fraction of inputs? Can you do it for 99% of inputs? Okay. That's actually equivalent to what we today call average case hardness on the uniform distribution. Right? So we'll say that something, okay, does there exist an algorithm that computes it with today we define average case hardness as the probability we can compute something with a randomly chosen x from some distribution, and if you let this distribution be uniform, that's exactly the same thing as with what fraction of inputs you can compute it. That's actually a notion introduced by Levin later on. And so today we're going to talk about the average case hardness of this problem. Okay, we're going to talk about it over general distributions, but also over the uniform distribution. In fact, the key result is going to be with respect to the uniform distribution, so it actually goes back to exactly the question they looked at. Okay, we'll say that KT is mildly harder than average over a distribution D if there exists some polynomial P such that no algorithm is able to compute it with better than 1 minus 1 over P. So think of P as n squared. We're saying there's no algorithm that can compute it. You know, it can compute it with 99%, but you won't be able to do it essentially always. Right? There is a polynomial fraction of inputs on which it needs to fail. Okay? So this is the type of notion of hardness that we typically consider in cryptography. There's no algorithm that succeeds with, well, that succeeds, but this algorithm is allowed to make mistakes. Okay, so this is sometimes called two-sided error hardness. In the complexity theory literature by Levin also introduced a different notion of average case hardness. This has nothing to do with Kolmogorov complexity, but it will be useful for later on to go over this also. There's this notion called errorless average case hardness. So errorless average case hardness, I'm considering an algorithm that's supposed to solve some problem, but this algorithm needs to either give me the true right answer or give up or give a bot. He's not allowed to make any mistakes. Okay, so we can say that a problem is errorless hard if there is no errorless algorithm that is able to solve it. And it's again, as before, it's allowed to, now it's no longer a mistake, but it's allowed to give up for a polynomial fraction of the inputs. Okay. So errorless average case hardness is weaker than this because it's, and this is still stronger though than worst case hardness, because worst case hardness you don't make any mistakes. Any questions? Now it's interesting, like in the world that we live in, the way we do tests is typically like this, right? People write their exams, and when you get it right, you get a point. When you get it wrong, you get 0, but it doesn't kill you, right? Maybe we should start scoring things like this, actually. In the world with ChatGPT there, maybe this is the way to do it, to make sure that people are not copying, at least homework problems, right? To make sure people are not copying. Like, if you make a mistake, boom, you get 0 on the whole thing, okay? So don't, don't provide solutions that you don't know they're fully true. So that's the difference between the two. You can also consider this decisional version of the problem. The decisional version is just, I give you an instance, and I tell you a number, and you're supposed to tell me if the Kolmogorov complexity is bigger or smaller than a number. And that's often called the MKTP. I'm going to kind of use these things interchangeably. Sometimes I'm going to write KT when I really mean this thing. But you should be aware there's always the computational and then the decisional versions. OK. So here's the outline for today. We're going to spend most of the time in the private key setting. Okay, and we're going to first show that average case hardness of this problem with respect to the uniform distribution is equivalent to one-way functions. I'm not going to go dig into the details of the proof, but I'll try to kind of tell you the key conceptual insights that we get from that. And those insights have proven actually very useful in lots of different other things. Then we're going to next move on to the question is, can we do it based on worst case hardness? This is a much harder question, and there's been a lot of recent progress, and I'll try to kind of give you some highlights of that. Next, we're going to move on to just pure complexity theory. We're going to try to study these old questions from the 60s, the parabolic conjecture and NP completeness. Okay, so I'm going to review what's known there. Surprisingly, we'll see actually that there is some cracks into the parabolic conjecture. At least in a non-uniform model of computation, we can now actually break the non-uniform parabolic conjecture. That break turns out to rely on a connection with cryptography. Okay. So Chef is not here now, but yes, or a few days ago when Amit gave a talk on obfuscation, she was asking, are we aware of any scenarios where this win-win that we talk about in cryptography has actually played out and became a win, where we broke the scheme and that broke the assumption without us knowing how to break the assumption? As far as I know, and after I talked to Shafi, she also didn't know of an example. This might be the first example where that actually happens. So we're breaking this one function that we construct, and that break on the one function actually gives the first break on the Kolmogorov complexity problem. And still, we have no other direct attacks on it that don't pass through the one function. Okay, so we'll discuss that a little bit, and then we'll turn to the question of NP completeness. It's a complicated question. There's a lot of result in one direction, getting closer, and in the other direction, getting further. There are some deep connections with the notion of I/O here, and I hope that you will enjoy that. The kind of conclusion there is going to be whether we believe this is NP complete or not is pretty closely related to whether we think I/O is possible or not. Okay, and we'll discuss it. And then we'll move on to key exchange and towards practice. I'll do this pretty fast. All right, so let's jump in and talk about private key encryption. Okay, I'm not going to talk about private key encryption. As you know, I'm going to talk about the notion of one-way functions instead. One-way function is this very fundamental notion in cryptography. Iftar gave 2 hours about it already. So it's a function that's easy to compute efficiently, but it's hard to invert. Classic example, multiplying numbers, easy, factoring, hard. As you heard in Iftar's talk, one-way functions are known to be not only sufficient, but also necessary for lots of different things in cryptography. I already mentioned private key encryption, but lots of other things like digital signature, authentication schemes, PEGs, pseudonym generators, PRFs, commitments, and so on and so forth. Okay. There's also zero knowledge here. Okay, I put a little asterisk because we typically say that one-way functions and zero knowledge are equivalent. Not exactly true. Okay, almost, and we'll get back to that question. In fact, using this kind of point of view, we'll get more insight in that also. As you know, one-way functions are not equivalent to key exchange or public key encryption, as far as we know. Okay? And this is a major open question. In fact, I am pretty hopeful also that this whole paradigm will tell us a way to actually go from one-way functions to public key encryption also. I won't really have time to talk about it, but again, the techniques we have really seem to overcome at least the barriers that we currently know for this. Safe to say, at least from my point of view, whether one-way functions exist is the most important problem in cryptography. Without it, none of these things work. Of course, if we have quantum computers and quantum channels, maybe we still have something to do. But in the absence of that at the moment, this is really central. Okay, so this is what we're going to try to kind of give you an outline of. Again, I won't go into the details of the proofs, but I'm going to stay on the concepts and how they can be applied elsewhere. So I would like to show that one-way functions exist is equivalent to the time-bounded Kolmogorov complexity being hard on average. And here, hard on average, I mean with respect to the uniform distribution. Okay, so note, this is a very specific, explicit problem and a very simple, the most natural distribution. It's exactly the problem that they were looking at in the 60s. What fraction of inputs can I solve this on? Okay, so since an equivalence, we're going to first show how to build a one-way function from the hardness of this problem. And then we're going to later on show how to get from a one-way function the hardness of this problem. Now, this direction from one-way functions to hardness of Kolmogorov complexity is not entirely new. In fact, there were results already in the late 90s, this famous result by Rafael and Rudig, and in particular their paper on natural proofs, that actually contained a version of this. What they showed, and we'll discuss it later on, is that in fact one-way function implies worst case hardness of this problem. So that's going to be a stepping stone to us showing that it actually implies average case hardness also. Okay, but first direction. We want to show that if Kolmogorov complexity is hard, then we have one-way functions. We're not going to do it directly, but we're going to pass through this notion of a weak one-way function. What's a weak one-way function? Well, a weak one-way function is a function that's efficient, computable, but it's mildly hard on average to invert. So instead of being fully hard, there is no algorithm that is able to do it with probability 1 minus 1 over p of n for some polynomial. Okay, so it's exactly the analog of mild hard on average, just for one-way functions. And we know from Yao's famous result that if we have a weak one-way function, we can get a strong one-way function, parallel repetition. As Iftach mentioned, and we'll discuss later on, this is actually a pretty major bottleneck if we want to get really, truly practical constructions. We'll see this one-way function we get there, not bad, okay? This is the main bottleneck. So I would like to also highlight this question that Iftach mentioned. Can we do this better? If we can do this better, this could give us much more practical instructions based on this paradigm. And it's quite surprising that this, silly thing is where the bottleneck is to get something practical, that we don't know anything better than parallel repetition. Okay, here's the construction. Okay, the construction is actually very easy. So remember, I want to construct a one-way function. A one-way function takes some input and needs to generate an output. I take my input and I view this input as being made out of two parts. First part, I'm going to call it the program, and the second part is an index I. This index is log n bits. Okay. There's a little nuisance here. I'm going to need this in the formal construction. This is not going to be exact log n bits. It's going to be log n plus the c, where c is this constant of the overhead for Kolmogorov complexity. Okay, I said that Kolmogorov complexity is never more than n plus c, the length of print. Okay. So I'm going to in fact take the first part to be n plus c bits, and the second one is going to be an index. Now what I do, I take this index and I jump to that position in the first part, and I chop it off at that point. Okay, so I take my original program and I chop it up after position I. So now I have a smaller program. Okay, take this smaller program and run it for n square steps. This program will generate some output. Maybe it will, maybe it won't, but whatever it outputs, I take it. I take its output and I output it together with the index. That's it. You don't need this for n square, for t to be n square. You can let t to be something linear. So this is actually very practical, as is. But it's only weak, so that's why it's we lose in efficiency. So we'll try to argue this is a weak one-way function. Now, to argue it's a weak one-way function, I want to show that if there is someone who inverts this thing, I can solve time-bounded Kolmogorov complexity. Okay, so assume that I have somebody who's able to invert it, and I would like to show you that I can, in fact, solve time-bounded Kolmogorov complexity. For simplicity, let's assume we can do it to probability 1. Okay, there's an attacker that does it with probability 1. In that case, this would be dirt easy. Anyone wants to do it? So I get a string x. I would like to determine its Kolmogorov complexity. What do I do?
Try all the odds.
Yeah. So I get a string y. Let's call it a string y. I get a string y, and now I would like to determine its Kolmogorov complexity. I take y and I concatenate 1 to it. And I ask this guy to invert it. What does it mean to invert it? Inverting it means I'm finding some big program, whatever it is, that if I chop it off at position I have some smaller program of length I that is supposed to generate y. So if it's able to invert it, I found a KT witness, we call it, a program of length I that is able to generate a string. Done. So now I just go over all the possible indexes, and I've solved it. I just picked the smallest one. So this seems to be really quite trivial. And now the issue here is that we don't really have somebody who does it probability 1. We have somebody who only does it with high probability, probability 1 minus 1 over P of n for any as big P of n as I want, but still it's not probability 1. And in fact, then it's not so trivial anymore. In fact, this argument I just gave you before, you can do something similar for SAT. That's typically a homework problem many of us have, to construct a one-way function, worst case one-way function from SAT. It's quite easy. Just take a formula and a witness, and then output the formula and 1 if it's correct and 0 if it's not. And you can do the same type of argument on that. Okay, so you can get a worst case one-way function from SAT in the same way as here. The question here is, can we get something that's actually secure also in the average case setting? And here it's a little bit trickier. Okay, so we're going to do the same thing though. The reduction is going to be exactly the same. And intuitively, if it succeeds with high probability, the errors maybe shouldn't add up so much because I'm only querying it on n things. So by union bound, it should be fine. That's very misleading, this argument. And the issue is that it's not just about the number of queries I make to him. They correlated, sure, so that's very bad already. That's not the main thing that's bad. The main thing that's bad is that this attacker, he's able to invert it on outputs of the one-way function. Outputs of the one-way function, what are they? This is where he works, okay? I is some random string, and y is the output of a random program. That's what he's supposed to do. So he's able to invert it when y is the output of a random program of random length. But where do I run him? I run him on a uniform string. That's where I want him to work. And do random programs output random strings? No, they don't. We have all tried to program sometimes. Maybe we don't write random programs, but some of us are not far away. They don't still output random things. They're very far off. Okay, so this shouldn't work, but it does. Okay, and I'm not going to go over the proof, but let me tell you again, the point here is I'll try to give you the concepts. There are two key ideas here that make it work. Okay, and the first one is this function that we came up with is length preserving. So what I mean by that is that it takes a Kolmogorov complexity instance and it embeds it in this one-way function in a way that does not blow up the input. Okay, we're only adding like log n bits, this little index I. That's very, very little. Okay. That's, if you contrast it to what happened with SAT, very different. SAT is, the construction from SAT is not length preserving. You lose a factor 2. Okay, that's actually a very, very deep difference. And I think it's a great question to try to come up with a length preserving construction, worst case one-way function from SAT.
Does this part of the proof use the Levin tricks, where a random if there's some good program, you're likely to hit it with something?
No, there's no tricks like this at all.
Not like this part.
No. Yeah. No, those tricks never appear actually.
The other side, right?
No.
The uniform, yeah, I don't have to get the uniform.
We'll get the other side, okay? The second thing is that random programs of length n plus c do actually hit all strings of length n. So these distributions are not the same, but they're not crazy way off. At least they have the same support. So why is that the case?
Print.
Yeah, add print to it, and you can hit everything. So support is right at least. In fact, by a slightly more fine-grained argument, you can show that not only support is the same, but in multiplicative distance, they're not too far off. And that's actually good enough. Okay, so that is the key trick. You want to show that this distribution is actually close in multiplicative distance, and that's actually fine. Then you can actually argue that if he fails with big probability here, he's going to fail with it's roughly the same probability here times the difference in the multiplicative gap. So this multiplicative distance argument is something that is sometimes used in cryptography, but it's not very, very common. It's happened a little bit in parallel repetition, but it's yeah.
Where does the length preserving thing come?
The length preserving.
The multiplicative thing.
This is exactly to make the multiplicative the thing go through.
Okay.
We're relying on length preserving property. That's actually the crucial thing, to show that the multiplicative distance is. Okay, in fact, like a simple special case of the proof can be shown on this slide. I'm not going to do it because it's a little bit tedious, but it's actually very easy to show the multiplicative distance. Okay, so we've shown one direction. One-way functions imply hardness of, or KT implies hardness of one-way function. And now we're going to show the other direction. Okay, the other direction was that if we have one-way functions, we want to show that KT is hard on average on the uniform distribution. Okay. Now, as I mentioned, this is not an entirely new result. In fact, early results going back to Rafael and Rudish show that one-way functions imply worst-case hardness of this problem. Okay, so that's going to be our starting point, and let's go over this slowly. We're going to eventually progress. This is going to be a lot harder. Okay, and I'm not going to go over all the details here at all, but we start off with going from one-way functions to worst-case hardness. Then I'm going to, as a second warm-up, go to errorless average-case hardness, which is still not good enough for us. And then we're going to, with a lot more work, go to actual average-case hardness. Now, just to point out, for this result, you don't need to pass through errorless average-case hardness. But I'm going to do it anyway because it's going to be very helpful for some other later results. Okay, so it's going to show us some key ideas that we need to do other things later on. Okay, so how do we get hardness from one-way functions? Now, the idea going back to Rafael and Rudish is that one-way functions we know imply PAGs. Iftach gave an hour about this, first hour. What is a PAG? A PAG is a function that takes a small seed and expands it to something long that looks random. So it takes a small uniform seed and expands it to something that's long, that's indistinguishable from random. And we know, based on Hill and all the improvements that Ifta talked about, how to get it from one-way functions. Good. Now, what Rafael and Rudish and this later works showed more explicitly was that if you have some algorithm that breaks MKTP or computes KT, then you can break a PAG. And if you can break a PAG, you can break one-way functions, and we're done. Okay, it's super easy. Let's do it. So here's a lemma. If you have some PAG that maps some S7-bit string, in that case, MKTP like this. Okay, so what I mean by this notation is MKTP when I have a threshold of S. So I need to determine whether it's bigger or smaller than S plus something. Okay, so I have this PAG that takes an S-bit long string and expands to something long. Okay. What does it mean to distinguish a PAG? I need to distinguish between uniform and the output of PAG. Now, a classic result, very easy to prove also about Kolmogorov complexity and time-bound Kolmogorov complexity, is that random strings have large Kolmogorov complexity. After all, that is why they introduced this notion, right? We want the random strings to have high Kolmogorov complexity, okay? And they do, very easy to show, okay? So if I sample something at uniform, the Kolmogorov complexity is going to be more than n minus, let's say, order log n with very high probability, okay? So here, the Kolmogorov complexity is very, very large. If I look at the output of our PAG, what is the Kolmogorov complexity? Tiny. Why? Well, it's S of n is the length of the seed, and it adds some constant for the time for the size of the PAG. So here it's tiny. We're done. Just run our algorithm. This guy, if I set it, he's going to say 1 always. This guy is going to say 0 always, at least if n is sufficiently big. That's it. Pretty nice. Sorry?
Why is G constant?
Which G constant?
Description of G.
G is a uniform, PG is uniform. Ifta described it to you. No?
Doesn't
Okay,
increase
so
with the
problem.
size of input.
A PG is a uniform algorithm.
I think that n is like runs to infinity.
Well, PG is a uniform algorithm that works for all input lengths.
Oh, I see.
All our algorithms are uniform. It means that they are constant descriptions. Okay? Very nice.
Only shows that orthogonal compensation problem is hard on the PRG output. Maybe it's ECR outside the field.
Okay, so now we're talking about average case hardness?
Yeah.
Okay, exactly. Well, right now, they only claim this worst case hardness. In fact, it wasn't really clear what the right answer should be. Let's move on to average case hardness, okay? And see what goes wrong. So if you look at the average case hardness, now I have this heuristic that's going to succeed with some decent probability, 99.999, very good probability. So when I run him here, well, everything's fine because he's a heuristic that works with high probability on uniform distribution. So here's going to output 0. No worries at all. What happens here? Manoj can answer now. What happened? I don't know. I think he's going to answer 0 because he's an asshole. This guy, that's the whole point of him, right? So he's an attacker. We don't know how to deal with him. He's going to output 0. Can he output 0 here? He can because they are very, very, very sparse. Okay, he can output 0 on all of them and be completely correct on everything else. Okay, and still be correct with 99.999, right? So this doesn't quite work. So can we get around this problem?
You could make S of n be very large, and this should still work, and then it's not that bad.
I don't understand that.
What if you take S of n to be n minus order log n?
It's still, you know, not. We will actually do that later on, but it's still not clear that that's going to, because this is S of n doesn't mean like it's pseudonym things could be very, very sparse still.
In fact, the smaller the sparser.
Typically, we want it to be very sparse. Yeah, and that's like the, yeah. But even, well, that's a good suggestion, but it doesn't, you know. Now, the first observation here, and this is actually goes back to work by Hirahara. He did it implicitly, and then we wrote it down explicitly. It's a very simple statement, super useful, okay? If you have a PG, then that's actually going to give you errorless average case hardness. What is errorless average case hardness? Remember, I have this attacker that's going to, or breaking errorless average means you have a heuristic that's either going to give it the correct thing or bot. So here, I know from before, this doesn't change. He got with 0 with high probability. Here, he either outputs the correct thing or bot. So now, can you break the PG? Yes. If you output 0, you say that. If it outputs 1 or bot, you say that, and done. Okay, so it works. So in fact, Raspberry Rudish with a extra one-liner actually gives us also average case hardness. Okay, all very nice, but we don't want errorless average case hardness. We want actual average case hardness, and that we don't know what he's going to do, and he can do whatever. Okay, output impact 0, and indeed we're going to take his suggestion. That's going to be a good starting point, but it's not enough. In fact, what we'd like to make sure is that this PG is going to be dense in this set. If you can show that it's dense in this set, in fact, it's going to be enough that it's dense in a multiplicative fashion, then that's going to be good enough. How do we make sure it's dense? Well, what we want is something we call an entry-preserving one-in function, entry-preserving PG. It's a PG that takes a C that's not too small. It's going to be n minus log n, exactly like you suggested. But this PG needs also to make sure that it preserves the mean entropy. So the output needs to still have good mean entropy. Okay, in fact, you should have roughly the same mean entropy as the length of the seed. And if you do that, then in fact, you can show that it's going to give you average case hardness. Okay, so you have to have an entropy preserving PRG, you actually do get average case hardness. Okay, so what is an entropy preserving PRG? Exactly as I mentioned, it's a normal PRG, and additionally, G of U of n should in fact have entropy n minus log n. It does not lose entropy of the seed. And now, again, I'm not going to give you a proof, but the proof is actually surprisingly similar to the previous direction. Because what does it mean to have mean entropy? That means that your multiplicative distance is not too high from the uniform distribution. And in that case, we can actually show that like this thing is going to still not output one with high probability, but at least with 1 over poly probability, it's going to do it. And that's still good enough. Okay. Now, we just need to construct an entropy preserving PRG. So let's go back to how we construct PRGs. And at first, we're very happy because we go back to Oded's book and look at constructions of PRG that we learned in school. And what do we see? Well, let's start with one permutations, because that's easy. We can all understand that. Just one permutation, Goldach-Levin. And look at it. This thing preserves all entropy, because the first part here is just a permutation of a seed and some random thing, fully preserving all the entropy. Awesome. This thing is entropy preserving. So great. We've now shown that one permutations give you average case hardness of MKTP. But we wanted to get the one functions. And then we have to look at Hill or Iftach's thing. We don't know. In fact, still an open question whether these are entropy preserving. It's very complicated to understand what goes on.
No, because
You don't even need to expand.
I cannot do parallel. What?
not entropy preserving. So the question whether you can take another construction to them.
We know they're exact.
Not entropy preserving.
I guess they're not. Yeah. But maybe there's a way to. Yeah. What is it?
Since the PRG is so weak, you just need to expand it by a little. Then it seems that you can.
That's always the case for all PRGs. PRGs only expand by 1 bit, and then we can expand it out.
No, but I mean, the entropy preserving, I can take like most of my seed and just copy paste and this.
All PRGs, you just need to expand by 1 bit. If you can expand by 1 bit, you're good enough.
No,
That's all
what
it
he's saying is that you could just make most of the PRG an identity function. And then that way you get a lot of entropy.
Yeah.
And then just expand the last bit. Is that what you're saying?
Yeah.
You're still going to lose a lot. Like I need to make sure I only lose log n.
So I'll take the last low then.
You're still going to have to apply a PG at some point.
Yeah, then.
Still, well, to log n bits is not going to be secure. Yeah. No, you can do something like that if you are so complex to leveraging. You can do something, but then you get something really ugly. Okay, so before the break, let me tell you the key insight that gets you around this issue. Because here we're stuck for a while because it seems like an unsolvable kind of issue.
You just set the universal hash function or something like that?
Then we would construct it. It's still an open problem, how to get an entropy preserving PG. A great open problem, how to get an entropy preserving PG from one functions, we still don't know.
And what is the best bound that is known in terms of entropy preserving PRGs from PRGs? Because you said that.
I think, if you do this kind of padding tricks, you can always get it to be like you lose n to the epsilon. So there are some trivialities you can always do. So I don't think we know anything better than trivial. Okay, and we'll get back to why this is interesting later on, actually. So here is the key insight, okay? This is a really, really simple, almost trivial insight that's going to be super powerful, not only for this, but for lots of other things. The point here is that this whole paradigm from Raspberry Rudish was, let's construct a PRG, and that's where we're trying very hard. We don't need a PRG. PRGs are overkill. Okay? We need a weaker object. Okay, and let's look at this picture. In a PRG, there are two things that are efficient. The PRG is efficient, and the input to the PRG, which is uniform string, is efficient. In this picture, I don't care about the input being efficient. I can sample this from any distribution I want, okay? And that still will give you hardness of MKTP. So if you can just find some kind of, we call it a conditional PRG, which is hard on some input distribution of a seed, then this still works. Why? Well, here we didn't even use it on this side. And here, I don't give a damn where this come from as long as it's short. So that's all you need. So you need a conditional PRG. Okay, so you can define a conditional PRG as looking at the distribution being from something else, or I can look at it as uniform conditional something. This is how we did originally. I think the better way to look at it now is according to on some input C distribution. It doesn't really matter. I'm leaving it like this because that's how it was in the paper. But basically what I just mentioned here is that conditional PRGs imply worst case hardness and in fact imply average case hardness directly. Okay, the same argument exactly didn't change. And if you have an entropy reserver one, then it's going to also give you that too. So you don't need a real PRG, just need a conditional one. Now, why is conditioning powerful? Okay, so I'm not going to give you the whole thing, but let me give you an insight. And here is a kind of a warm-up that is still very, very intriguing. There is this thing called an auxiliary input one-way function, which roughly speaking it's a one-way function computable by a circuit. Okay, think of it as a non-uniform one-way function. It's actually a little bit weaker. It says that for every attacker, there exists a particular circuit that computes something that tricks this particular attacker. But for now, for simplicity, just think of it as a circuit computing a function. So it's not a uniform function. Can we get average case hardness from this kind of auxiliary input one-way functions? It's not completely trivial. I think Salil had some ways of doing it. Let me give you a one-line proof of it. Okay. An auxiliary input one-way function, I can use that in a trivial way to build a conditional PRG. How? Take this one-way function, apply HIL to it. Okay. I'm going to call that GZ, where Z is this description of the auxiliary input. And now look at this bizarre thing, a bizarre uniform function, which just takes a seed and a random string. I'm going to hope that this random string is going to be the auxiliary input, and that just runs it. Okay. This thing, as we know, we can do PRG expansion, so this PRG can expand as much as you want. So I can make sure that this input is much smaller than the output. Are you with me? So I'm just taking this auxiliary input one-way function, and I'm constructing a PRG using HIL from this thing. Now, the key thing here is that this function, I claim, is a conditional PRG. Why? Condition on me sampling the right auxiliary input, it's a PRG by definition.
But it's not entropy preserving.
No, it's not entropy preserving. This is just to explain to you that conditioning allows you to do something pretty magical. It allows you to get a PRG from something that's much weaker, in particular this. Okay, and so
Hardness Kolmogorov complexity for that? No.
So as a corollary,
Yeah.
you get that auxiliary input one-way functions imply average case hardness of errorless average case hardness of Kolmogorov complexity, which is like pretty non-trivial. So auxiliary input one-way functions imply errorless hardness of this.
But this is not sufficient to get one function again.
No. So to get one-way function, we need to construct something that's entropy preserving. And that I don't know how to do from auxiliary input, which would be fantastic if we could do. But in fact, I won't do it here because we all want a break now. But Iftach provided a construction from of PRGs from regular one-way functions. Okay, that was his like starting point. And then he said, okay, like to make it work from normal one-way function, we need to kind of guess the regularity and mess around like that. That was the HIL construction. Now I'm going to in fact take kind of a variant of the first step there and make the observation that every function, I can decompose it into a bunch of regular functions. Right? That was what Iftach called the degeneracy. Okay? So for each input, there is the degeneracy of the input, how many pre-images it have. And I can just take this one-way function, split it up into these many different regular one-way functions on its on the domain. Okay? So one of them must be pretty happy with probability at least one over n. If I condition on my input coming from that particular domain, okay, And I'm also going to like guess to have that be part of the degeneracy, be part of the input. So if I condition also on that, condition those two things, I can use what Iftar said. So in fact, take any one function, do this construction that does not work, but conditioning on the right events, it will be a PG.
But still you need to lose something about entropy, you know, like.
Okay, so if you do it carefully, you actually turns out that if you look at this construction, you don't lose on entropy because there's a bunch of extractors conditioning us guessing correctly. This is going to be statistically close to uniform. And if it's statistically close to uniform, you can argue that condition on something else, it's going to actually be actually have mean entropy. So you can still condition on something else, you lose a factor 2. Tedious calculations, but therefore there is some event I can condition on. In particular, this thing of like guessing the right degeneracy. In that case, this actually will be entropy preserving. And that gives the whole thing. We'll take a break now, and then I'm going to come back to kind of these these insights we learned, and we're going to use them to apply them. So this was kind of the warm-up, and then we'll play around with these things.